Okay, here we are. This is probably the last physics video for the semester. We want to look at the second half of 8.2. We're going to look at moment of inertia. Inertia is the resistance of rotation or resistance of movement of any time, and we're talking about rotational dynamics. So the moment of inertia is going to be measured in how hard it is to get something to spin, and we're going to be able to relate that then back to the acceleration. So, if you want to see a little bit about what we're talking about here, if you take a pencil, imagine taping two coins on the end of the pencil, and then just try twisting, wiggling it back and forth between your fingers so that you're trying to get it to spin a little bit like a mini baton. You could see that it would have a certain amount of resistance to move. If you then move the coins in, uh, so that they're really close together, they're right next to your fingers, and you try to wiggle the pen now, you're going to find that it wiggles real easy. We've just changed the moment of inertia. We haven't changed the mass, same coin, same pencil. We've just changed where the mass is. So we could find out that the amount of mass is not the only factor that is going to determine how much torque it takes to change angular acceleration. We also need to know this idea of moment of inertia. The resistance to rotation is called inertia, which is represented by the symbol I. It has the units of mass times the square of the distance. So that's what we're going to be looking at, mass in kilograms, distance in meters. So our units are going to be kilograms per meter squared. You could see here there's a variety of um, formulas based on the equation. I think it's a little bit clearer in the next slide. So for instance, if I have a thin hoop, looks like that, then the location of the axis is simply through the middle, and the formula is pretty straightforward, mass times the radius squared. If I have a solid cylinder, like a coin or a big wheel or something like that, again, the location of the axis is through the center, and now I have half the mass times the radius squared, because the mass is now distributed all along from the outside to the in. If I have a sphere, the axis of rotation down through the middle, I now have a different formula. It ends up being 2/5 mass times the radius squared. And again, you'll know I'm going to be giving you these formulas if you need to use them. If I have a long rod, solid rod, not a baton, but a solid rod, then again it passes through the center, and it ends up being 1/12 times mass times the I, which is the length of the rod now. And a long rod, um, uniform rod, if we're going to spin it from one end, our I changes a little bit. The length of the rod is now from there, and the formula changes to 1/3 the mass times the length of the rod squared. Length of the rod is going to be measured in meters. If we have a thin piece of material like this, axis through the center, we have L and we have the width. Okay, we have to kind of, looks like almost an area formula here. It's 1/12 times the mass times the length squared plus the width squared. So that's how we're going to be doing our calculations. We'll use one of these formulas for doing calculations. All right, continuing on. Okay, so for example, for a point that's located a distance r from the axis of rotation, the moment of inertia is given as I, which is the moment of inertia, where the inertia it will be equal to the mass times the radius squared. That's going to be our first one. The moment of inertia is a point mass. Try that again. The moment of inertia of a point mass is equal to the mass of the object times the square of the distance from the axis. So that's the equation that we're going to be using. Again, we could look at a textbook. This would not be the last equation. This would be probably more similar to, well, one of the other equations anyway. But just to give you an idea, if you took the physics book and you held it at the end, you'd see it's kind of hard to rotate. If you held it right in the middle, It's a lot easier, a lot less torque required. So again, we could tell based on this that it's going to make a difference of where our the axis is, where the axis of rotation is, even for the same object. So repeat it within the middle, less torque is needed. That's all they're saying there. Okay, so let's try a problem then. Simplified model, we're twirling a baton. It's a thin metal rod with two round objects on each end. The length of the baton, 0.66 meters. The mass of each object is 0.3 kilograms. We want to find the moment of inertia of the baton as it's rotated about its axis at the midpoint between the objects, so right in the middle, just a standard baton, and what is the moment of inertia of the baton if it's moved at one end of the rod. And then the question then is which one's going to be greater. We're going to assume that the mass of the rod itself is negligible. In other words, it doesn't weigh a whole lot. We're really just calculating for these objects. Makes the problem a little bit easier. So here we sketched it out. Here's your baton, mass at both ends. We're going to try first of all this one where we hold it in the middle and spin it. And then the other one we have the axis of rotation at one end and we're just spinning the other end. So this weight actually kind of goes away. We're just going to be spinning this weight at 0.66 meters away. Here we have two masses that are half the distance. We want to figure out which one is greater than, or if they're equal. So once again, we have our knowns, and here we have a length. I is the moment of inertia. L is length here. I is the moment of inertia. So we're going to be doing these calculations. So if we're going to solve for the unknown, we're going to calculate the moment of inertia for each mass separately. So the first thing we have to do is, if we're rotating around the center, we need to figure out what the radius is, which is simply half the length. So that if the length is 0.66, half the length is 0.33. So each mass is 0.33 meters away, and each mass weighs 0.3 kilograms. So the mass of the moment of inertia for a single mass would be the mass of the object, 0.3 times the radius squared. And we get, multiply all that out, 0.033 kilograms per meter squared. So that's the units. But we have two masses. Each one is 0.33 kilograms away. So each one has a moment of inertia of 0.33. So we're going to double that. And we end up with, for holding the baton in the middle, 0.66 kilograms per meter squared. So what about if we rotate it around one end? We only have one mass that we're worried about. The other mass is in our hand. So we have the mass times the radius squared. The radius squared is now the full length of the rod. That's how far the mass is away from your hand. So now you're just going to plug in 0.3 times 0.66 squared. When we multiply all that together, we get 0.13 kilograms per meter squared. A lot bigger than if we're holding it in the middle and spinning it. It takes a lot more force then to spin it around. So the moment of inertia is greater if the baton is swung around one end than it is if we hold it in the middle and we want to twirl it. Just evaluating your answers. It looks like our units are correct because the unit should be kilograms per meter squared. We got that. Does it seem realistic? It says masses and distances are small, so the moments of inertia are going to be small. Doubling the distance increases the moment of inertia by a factor of 4. Thus, the doubling the distance overcomes having only one mass contributing. And we sketched it out. We solved for the unknown. We evaluated our answer. So I said that we could use this to figure in acceleration, which basically brings us to Newton's second law of rotational motion. So he has a bunch of laws. This is a law of rotational motion. It states that the angular acceleration is directly proportional to the net torque and inversely proportional to the moment of inertia. So let's take a look at the equation down here. The angular acceleration, how fast we could spin something, is going to be directly proportional to the torque. If I increase the torque, I could spin it faster. The harder I spin it, the faster it goes. That makes sense. That's the torque. Now, the other thing, though, is a moment of inertia. Is that moment of inertia moves away from the rotational axis. In other words, the further away it gets from the moment of, or the axis of rotation, the more we increase the inertia, the moment of inertia. And the higher the moment of inertia, the harder it is to spin something. Or for the same amount of torque, the slower it will accelerate. So that's our equation then. So angular acceleration then is going to be equal to the torque divided by the moment of inertia. If the torque on an object and the angular velocity of that object are in the same direction, in other words, we're trying to speed it up, then the angular velocity increases. So we're putting it's already spinning and we're adding more torque, we're going to make it go faster. On the other hand, if the thing is already spinning and we're going to apply torque opposite direction, then the angular velocity is going to decrease. We're going to slow it down. And that's pretty much it.